Okay, ready? So 6-9, we did not have, no homework was given. Yay, that was yesterday. 6-10, we are going to skip. It's not that it's not an important concept, it's just the group decided to skip it. So 6-11, I think today's title is kind of funny. It says one mean test, which it's a one average test, but it's one mean test, right? So y'all on page 40? All right, ready? So page 40, here we go. It says when a hypothesis test is required using means. Okay, so we're using averages. We use a normal distribution to calculate the p-value when we know the population standard deviation in real life is rare. We calculate the p-value using the t-distribution when the population standard deviation is unknown, because we must use the sample standard deviation as estimator of the population standard deviation. Whoa, that's a mouthful. Okay, so we calculate the p-value using a t-distribution. So t-distribution is a little bit different. We're going to be using the degrees of freedom again. Remember, degrees of freedom is your sample size minus 1. And degrees t-samples work when you have samples smaller than 30. They'll work for all of them, but as you get bigger and bigger, it gets closer and closer to a z. All right. So otherwise, the process is exactly the same as the process for the one mean z-test versus one mean t-test. Normality looks different. It's kind of a surprise that the t-distribution is not a normal distribution, even though they appear to be. So basically, if you were to look at one or the other distributions, I mean, they both look like normal curves. And I'm not going to say which one would be the z versus the t, but they're both normal-looking curves, but the one that is for the z-test is not, or the t-test is not a normally distributed thing. The one mean z-test normality assumption satisfiers either is the population is known. So z-test, we know the population. And then the sample is bigger than, the sample is bigger than 30. The one for the t-test, normality assumption is satisfied even when the whole sample size is very large or very small, as long as the sample is not sharply skewed and has no outliers. So as long as your graph doesn't look like this or like this, as long as you're not skewed or have multiple bumps. Hello? All right. So this is a judgment call worth noting that the t-test is very robust. That is, it works very well, even under conditions that are not ideal with small sample sizes. Okay? All right. So the following breakdown for the hypothesis test. We don't need to, we can kind of skip number 1, identify the appropriate hypothesis test, okay? Being that we're not worried if we're using Z versus T, you just know that if you're going to use, if the t-test is going to be used, you're dealing with a sample size that's below 30. Okay, state the null hypothesis, an alternative, we've done that. Create the null hypothesis sampling distribution, that's just making the normal curve. Calculate the p-value. But the p-value is actually going to be a t-score now. And then state the conclusion, or calculate the p-value, then state the conclusion, and then we're not going to worry about the assumptions. Okay? So I have one whole example there on page 41 that we can run through. Okay, now my goal is I have a review that we'll do tomorrow on up through 6:11, and then we'll do 6:12 on probably Monday, Tuesday. A little bit more review on Wednesday, and then I think Thursday next week. Or actually, I take it back. Let's see. Let me think about this real quick. So Friday, we will do a review. And then Monday, we will do, let's do this. We will go over the review very well. Tuesday, we have up to a 6:11 quiz, which goes along with the review. Wednesday, we'll take care of 6:12. Thursday, we have review for chapter test. And then, I don't remember, Friday next week, we would probably continue the review. The Monday afterwards, I hate to do it to you, we'll probably have test part 1. And then the Tuesday after that is test part 2. I think that's kind of the overall plan where I'm at. Okay. Okay.
Do you want me to send a picture to Rowan?
Yeah, I have it recorded. I'm sure she'll watch it. All right. So the example on page 41 says the average price of gas in Colorado is greater than $2.50 per gallon. Well, duh, we of course seen that, but this was done a few years ago. So when gas prices were manageable, yeah, me too. A random sample of 20 gas stations shows an average of $2.54 with standard deviation 30 cents, and then use alpha of 10. Okay. So oh my gosh. So let's create, we're skipping number 1. Let's go to number 2. So we have our null is this, and we're going larger. And then basically mu is the average price of gas. Okay. All right. So this one we will indeed want to set up the standard error because we're sampling 30 gas stations. So we know right now that we have an average of 250, or excuse me, 254. Sorry. Okay. And then we know we have a standard deviation of 30. So, but we want to find the standard error. So we're going to go 0.30 divided by root 20. And that's going to come out to 0.07 round. And the reason I'm rounded to 2 decimal places, we're dealing with money. Okay? They're saying the mean. So we're stating that the price of gas is $2.50 per gallon, but they found that our sample had a mean of $2.54. Okay, and then the standard deviation 30. But the reason we want to do the standard error is we did a random sample of 20 gas stations. So here's the big thing with the standard error versus standard deviation. We've talked about this a little bit. Standard deviation on a normal curve, your information is spread out. The more and more you take samples, the closer and closer to the mean that you're trying to get. That's what your standard error is doing. It's getting closer and closer to the mean. So you're talking about a smaller amount of area. So if I do my normal distribution, so we have 250, and then 257, and 264, and then go out one more just for fun to 271. Go this way, we go to 243, 236, oops, 236. And boy, it would be great if prices were still this.
236.
Yeah, geez, unbelievable. All right, so they're saying that this is based on our hypothesis. So then we have to think about where is that 254 going to fall here. That 254 is here. And then we're talking about this area over here. Okay, so now there's a new calculator command that we're going to go to. I have to bring up my calculator. So yes, it's there. Cool. All right. So before I get to that, go back here. So what we're going to do is we are going to do TCDF or TCDF is, I believe, what it is. This is the Z-score. That's something we haven't heard about in a while. And then we're going to infinity, so we're going, very large. And then we do our degrees of freedom. Now, once you know what these are, it's not hard to plug into the calculator. So how do I find the Z-score? Does anyone remember how to find the Z-score? So it's going to be over our standard deviation. Okay, so I'm going to take 254 and I'm going to subtract my null 250 or mu over the standard deviation, which we said was 0.07. So that's going to give me 0.04 over 0.07. Does someone have a calculator or on your phone? Just go 0.04 divided by 0.07 for me, please.
It's 0.57.
0.57?
Yeah.
Sounds good. Do we agree on that?
Yeah.
So this is my Z-score. So under my TCDF, I'm going to go 0.57, some large number, so 1,000. And then degrees of freedom is going to be my n minus 1. Well, my n was 20. 20 minus 1 is 19. Okay? Now we just have to find the TCDF. So I have 0.57 thousand or 10,000 or a million. Take that out there. And let's take a look. Let's find TCDF. So it should be under second distribution. TCDF looks like number 6 on mine. Oh, did I go the wrong one? Second distribution. That was TC. Yeah, Poisson CDF. Oh, wow. All right. All right, we'll go with number 6. Go with that. Oh, we have it. So our lower we said was 0.57. Our upper was going to be big, so we'll go 1,000 or something. And our degrees of freedom would be 19. Enter. So roughly 0.29. So if I do the math on the TCDF, this right here, I'm running out of room, is roughly, so it's going to be roughly 0.29. That becomes our p-value. Okay. Now, what do we say the p-value, if the p-value is larger than we fail to reject our null? 0.05. So if p is greater than 0.05, so b and p is 0.29, is 0.29 a larger number than 0.05? Sure is. So this, taking a look at that, this says I've went every which way on this page. We failed to reject the null. We didn't find strong evidence that the average price gas, we did not find strong evidence that greater than $2.50. And I know you all say, no, that's wrong. I drove by a gas station this morning. Heck, the one right down there is $2.56 a gallon or something.
It's like
It's 405 actually.
How much?
Yesterday.
405.
Thank God I didn't buy it though, because the air pump, like my tire was almost flat. But it was broken, so I didn't have to pay 405. Still paid the money.
Giddy up.
The arena is
All right, so there is an awful lot with this information. So I think that page on page 41, what I've written here, which I didn't go in wholeheartedly great order, but let's do this. Let's highlight. So this yellow here, this would be number 2. Number 3 is drawing this out. Number 4 is doing this and getting that. And then number 5 is that. Okay, so can I give you the opportunity to find where the homework is? Is that 6? Is it 6:11? Thank you. All right. All right, let's have you do, not an orange highlighter, page 117, 118, see how you do with it. Try it based on what we had just done. And if you need to do if you don't have the calculator, that's fine. Just do the TCDF. Just make sure you have the degrees of freedom and stuff in there. Get it done for